I'm ready.
Okay. Okay, can you see my screen? Okay. Okay, so this is the 5th group study of CS591, and the topic is Mastering Go Game with AI. We are group 8, including Yeonhee, Che, and Siri. This presentation delivers 2 Go game programs that defeat human professional players and achieve intelligent play. The first paper, Mastering the Game of Go with Deep Neural Network and Tree Search, is about AlphaGo that won a human professional player for the first time. The second player is about AlphaGo Zero that was enhanced version of AlphaGo. So I'm going to introduce the first paper. The contents will be a problem statement, training pipeline of AlphaGo, how does it work in practice, which one works better, and how does AlphaGo mean. So again, this paper is about the first case that the machine won Go game against a human player. The name of the machine is AlphaGo, which was developed by Google DeepMind. Go game was the most challenging field for developers due to a vast number of moves and positions. So this is the board for Go game, and we can only put stones on the cross lines, like here and here, as the image shows. There are approximately 250 to the power of 150 possible moves, where 250 means the number of accepted moves per state, and 150 means the average number of moves. It was infeasible to compute all the moves before, so the following question was how to reduce search spaces in Go game. And I will present how AlphaGo overcame the challenge. The solution that AlphaGo developers devised is the combination of neural networks and Monte Carlo tree search. The neural network model is a CNN, which is an abbreviation of convolutional neural network, and which is specialized in image and pattern recognition. The entire network layer, as I point in a red highlight pen, the entire network layers construct board positions. The previous works of Go games used MCTS, Monte Carlo tree search, as well, but it had a significant limitation. They depended on linear computation. However, with the advent of CNN, AlphaGo broke the limit because the CNN uses nonlinear computation and highlighted a new approach. The first stage of training is supervised learning of policy networks. Supervised learning have machines learn answers and maximizes the probability to choose the right answers by giving a set of questions and answers. Likewise, supervised learning policy network in AlphaGo has given board states and their corresponding answers. The board states include different types of states such as response, Atari, neighbor, and Nakade, which is the terminology of Go game. The policy network is trained to predict the next move of a human player. This helps the network to learn more promising moves. The mathematical formula for training the network is shown here, where A means all legal moves and S means the state. And the sigma means the weights of convolutional layers. In short, it learns sigma that maximizes the likelihood of the next move in the current state. The policy network provides a probability distribution over all illegal moves A in state S, as shown in the second left figure. Another important network is a rollout policy. It is a contracted version of the policy network so that it shows faster performance and lower accuracy compared to the policy network. The second key training algorithm is reinforced learning of policy networks. Ironically, it is problematic if the policy network makes good decisions on the basis of given sample data set. This would cause unsuccessful gameplay in practice. It is called overfitting a problem. If the neural network overfits data set, especially training data set, it does not infer a better choice in a new data set. This is similar to the fact that on a client, a sports player needs both practice and real game skills. Reinforcement learning means self-learning without any correct answers. It improves the supervised learning policy network that I showed earlier. To improve the earlier policy network, reinforcement learning policy network is initialized to the supervised learning policy network. Then games repeat between a randomly chosen of supervised learning policy network and the reinforcement policy network to update the reinforcement learning policy gradient P. The formula is following as shown in here. A reward function, this one ZT, which produces the outcome of a game. +1 means winning and -1 means losing. T means each time step. In other words, the formula, this mathematical formula, adjusts P depending on the likelihood of the final winning in the current state and each time step. The network learns from mistakes. The third training algorithm is reinforcement learning of volume networks. The volume network outputs a prediction of the winner from a board state. The weight of the volume network, theta, is trained by regression. Its purpose is to minimize the mean square error, which is this one, between the predicted outcome and the real outcome. The formula is shown in here. And it is important to prepare a new training data set. If the volume network is trained by complete games, it would rather memorize board states and their corresponding outcomes. This is overfitting problem again. The MSE, the mean square error on the training set was higher than on the test set previously. So the solution for the problem is that the reinforcement learning policy network plays games against itself to generate a new data set. Training on the new data set reduced the difference. So the mean square error on the new training set became 0.226, and the test set was 0.234, which means that the even value is a fine algorithm. And once the networks are trained, MCTS integrates them. MCTS is look-ahead search that simulates possible circumstances and traverse a more promising leaf per step. The MCTS algorithm in AlphaGo consists of 4 steps: selection, expansion, evaluation, and backup. Selection is to select a leaf that has a higher value of the addition between the actual value Q and U, which is proportionate to prior probability. In the expansion process, it expands other leaves by using the supervised learning policy network, which is P sigma, which eventually reduces the breadth of tree search. The probability is stored in the prior probability P. The evaluation process adopts the trained value network and the outcome of the fast rollout policy, P pi, which eventually reduces the depth of tree search. It simulates play at the end of a game and estimates the outcome. When lambda is 0, it only uses the value network. When lambda is 1, this is going to be eliminated, and it only uses the rollout policy. The evaluation process could be accurate by changing and finding the right value of the lambda. And the last process is backup. After evaluation, update action value Q and visit counts N by traversing all the edges back to the front to produce. This is backpropagation technique that adjusts gradient and produces a better result. Here's an easy example. An archer thought 45-degree will be the best angle to shoot the target, but then he or she learns above 45 degrees would get an arrow closer to the target after shooting. So the archer learns from the result repeatedly. So similarly, the backpropagation learns adequate Q from simulated results. And the next question is, which one works better? So there are several conditions in AlphaGo programs. So the first is between a single version of AlphaGo and a distributed version of AlphaGo. AlphaGo uses asynchronous multi-threaded search that divides responsible hardware into CPU and GPU. Neural networks such as policy and value networks run on GPUs, whereas MCTS, the tree search, runs on CPUs. This is a single version of AlphaGo. The developers showed that this version easily surpassed other Go programs, including Crazy Stone, Zen, Pachi, and Fuego. Even if the AlphaGo had intentional handicap stones, it still recorded high winning percentage, like average 87%. A more enhanced AlphaGo uses 1,202 CPUs and 176 GPUs. This is the AlphaGo that defeated Fan Hui, Chinese-French professional Go player. So a distributed version of AlphaGo works better than a single version of AlphaGo. And the next, the mixed evaluation provided the best performance, while the value network, when lambda is 0, provided the second best performance. So mixed evaluation works the best, and using only value network works the second best, and the last is using only rollouts. And the conclusion is, what does AlphaGo mean? So it wouldn't mean just defeat human beings. The way human play Go is to scan a board state, search the best place to put a stone, and think if it can bring them victory. AlphaGo was implemented to process the same steps. It searches positions by the policy network and evaluates them by the value network. Both networks are neural networks were trained by supervised learning and reinforcement learning. They are combined with MCTS at the end. This is the extraordinary feature of AlphaGo compared to the other remaining Go programs, which only exploit MCTS. The success of AlphaGo brought expectation that many AI domains could attain human-level performance. So my presentation is end here, and the next presenter will be Che.
Yeah, give me access.
Okay. Yeah, I just gave you the
Thank you.
access.
Can you see my screen, right? Yeah. Um, Now I'm going to discuss about the method, the policy of network classifications, and the reinforcement learning and volume network recursive and features of policy and volume and neural network architecture and evolutions. And some here some classifications and reinforcement learning and regressive. Policy networks means in the KGS data sets, we train the policy network P to classify the position based on the expert moves. These data sets contains 2.94 million positions from 1600 uh, 160,000 games played by the KGS. 6 to 9 than human players with handicapped games account for 35.4% of the games. So we sample a randomly selected mini batch of M samples from the argument KGS data set of each training set step and used the asynchronous stochastic guidance descent updated to the maximum the login likelihood of the action, and the step size was the set to 0.003 and was half after every 8 million training steps with no one terms and mini badges. It's going and like this, and the network reinforcement learning. Each iteration consists of mini batches of M games. So parallel between the current policy and network P is being trained. And then opponent P that uses the parameter from the previous iterations randomly. So like this, we are going to discuss the games were then replayed to the determined policy of updated with the algorithm 25%, 25 used for variant reductions with the baseline, and the value network reduces the a value of a function RL policy network P. We trained V of S and V of SP. We created a data set of uncontrolled self-plate positions to avoid the overfitting to the strongly correlated positions with the games. So we sample from distributing during the first two phases of generation, increase the diversity of data sets, and 50 million mini batches of 32 positions using the GPUs and other features and value network that are representing the game rules. They are indicated the status of each intersection of Go board stone colors, liberty, liberties, and captures. So done stone was played and the current color to play. All features were calculated in the relation to the current color is played. And neural network architecture, the first hidden layer 0 converted into input of 23 into 23 images and then and 55 sites like this. And I just explained the uh, how the architecture is developed, and I'm going to evolution. We just accept the relative strength of computer Go programming by holding an internal tournament and calculated each program. So we also played handicap games in which AlphaGo played with against like this. And with the exception distribution AlphaGo, each computer Go program was run on a single mission, which identically using the most recent available version and the best hardware configurations that supports. And so, and next I'm going to discuss about the mastering the game of Go without human knowledge. So how AlphaGo with zero and AlphaGo with zero training and AlphaGo zero lane analysis and performances of AlphaGo zero. A big AlphaGo recently became the first computer program to defeat a Go world champion. Deep neural network were used with AlphaGo research to evaluate the position and choose moves. So this neural network strengthens the tree search, resulting is better move selection and stronger self-played in the next iterations. So deep neural network trained by reinforcement learning have recently made rapid progress towards this goal. However, most difficult domains such as game Go, which widely grant challenges artificial intelligence. So the AlphaGo fan employed two deep learning neural network, a policy that generates move possibility was uh, value network generate position evaluation, and the network value was trying to predicate the outcome of policy versus the policy network games. And finally, it employs a simpler tree search and relies solely on the single neural network to evaluate the position and simple move with the uh, new learning reinforcement algorithm and incorporate look ahead search with the training loop. And this search has possibility of typical selections such as strong moves. Then the neural network is f of s and self-played with search selection, each move with improved mcts based policies. And as you see the figure one here, you see the performance of each person AST using the most recent neural network f of s. And uh, the neural network's parameters updated to the maximum policy of vectors of p of t's and t, as well as to minimize the difference between the predications winner vt and the game winner at z, as shown in the equation. And then next, zero for performance during the self played on this. So AlphaGo Zero made use of single AlphaGo. AlphaGo is mission with the four uh, transfer processes unit TPUs, and to compare with the benefits of self play reinforcement learning. To learn from human data, we trained a second neural network like this. And uh, the suggestion that AlphaGo Zero is developed by strategy that fundamentally different from human play, and using the fixed data of self-played games generated by AlphaGo with after 72 hours played each network, and knowledge learning by Zero AlphaGo. And we can see the figure 5 a figure here. Self-played one of the first element to go long ways to learn the human or understood much later with training the AlphaGo. Surprisingly, the latter captures the sequence that the span of entire border and go long ways learned by the human with understanding much later in the training by Alpha. And we learn next final performance of Alpha. This time is a large neural network, and for longer period of time during the 29 million of games played were tested, and all programs were given 5 seconds of thinking time for move in evaluation. AlphaGo Zero and AlphaGo Masters each played a single mission with 4 TPUs, and AlphaGo Fan and AlphaGo Lee was distributed across 176 GPUs. So finally, the AlphaGo Lee receives a rating of 3,739, and AlphaGo Fan receives the rating of 3,144. And that's my part.
Give me access to me. I will share my screen. Okay, thank you. Are you guys able to see my screen? Are you guys seeing? Okay, thank you. So, okay, coming to my point, I'm going to explain methods. So, there are so many methods. So, first one is reinforcement learning method, self-play reinforcement learning in games, AlphaGo versions, domain knowledge, self-play training pipeline, and optimization, self-play, and supervised learning. So, coming to the first one. Reinforcement learning is a policy iteration. So policy iteration is a classic algorithm that generates a sequence of improving policies by alternating between policy evaluation, estimating the value of function of the current policies. So classification based reinforcement learning, it improves the policy using a simple monoclonic search. So many rollouts are executed for each action. The action with the maximum mean value provides a positive training example, while other actions provide a negative training examples. A policy is that trained to the classify actions as a positive or negative. So a simple approach to policy evaluation is to estimate the value of functions from the outcomes of the sample transactions. So a simple approach of the policy improvement is select actions greatly with respect of the value of function, and policy improvement using the current value functions to generate the better policy. Uh, Also perform a policy evaluation by regressing the value functions towards the truncated rollouts value similar to the value component of AlphaGo 0. Also, self-play reinforcement learning in games. This approach is mostly directly applicable to the zero-sum games of the perfect information. So we follow the formalism of the alternating make over the games described in previous work. Nothing that algorithms based on the value of our policy iteration extend natural to this setting. Self-play reinforcement learning has previously been applied to the game of Go. So NeuroGo used it for the neural network to represent the value function using a sophisticated architecture based on the Go knowledge regarding the connectivity only. Self-play reinforcement learning approaches have achieved high levels of the performance in the other games like chess, checkers, Scrabble, other more recent pokers. Many of the most successful widely used reinforcement learning methods were first introduced in the context of the zero-sum games. So, AlphaGo versions. So we compare the three distinct versions of the AlphaGo. The first one is AlphaGo Fan, AlphaGo Lee, AlphaGo Master, and AlphaGo Zero. And AlphaGo Fan is we discussed so many machines using the 176 CPUs, and AlphaGo is it's introduced in the 14th March 2016. It is similarly most equal to the AlphaGo. However, we highlight the several key differences to facilitate the FIR comparisons. First, the value network was trained from the outcomes of the past games of the self-play by the AlphaGo rather than the games of the self-play by the policy network. The procedure was iterated several times, and initial steps towards the tableau happen. We will continue one more screen.
No, you can continue. 10, 9 minutes.
Okay, thank you. AlphaGo Master. The program is depicted to the human players by the human players. So Reinforcement learning algorithm and MCTS algorithm was described in the paper. So, however, it uses on the same handicrafted features rollouts as AlphaGo. So, fourth one is AlphaGo 0. It learns from self-play reinforcement learning, starting from the random initial weights without using the rollouts, without no human supervision, and using only a raw board history as input features. Then so domain knowledge, coming to the domain knowledge is our primary contribution of the demonstrated from the superhuman performance can be achieved without human domain knowledge. And AlphaGo 0 provide with the perfect knowledge of the game rules to stimulate the position resulting of the sequence moves. When both players are passed after the 19 into 722 moves, and AlphaGo 0 uses the yes. MCTS simulations and self-play training. This is the because of human scores. Like the input features describing the position structure was 19 into 19 image. So the rules of the Go are invariant under rotational and reflection knowledge is being used in the AlphaGo 0 both by augmenting the database during the training. It includes the rotation of and reflections of each position. And self-play training pipeline. AlphaGo 0 self-play training pipeline consists of three main components, all executed asynchronously in parallel. And neural networks parameters by I are continuously optimized from the recent self-play data. And optimization. Each neural network is optimized on the Google Cloud, so using a TensorFlow with a 64 GPU and evaluated. To ensure we always generate the best quality data, we evaluate each new neural network, check out against the current base network before using it for data generation. So self-play. And the best current player was we consider as the alpha theta star and selected by the evaluator is using to generate the data. In each iteration, players 25,000 games of the self-play using 1600 simulations of the each move, like how it selects the moves probably to the visit counts, like to ensure the self positions to encounter for the remainder of the game. And supervised learning. We also trained neural network parameters by supervised learning. The neural network architecture was identical to the AlphaGo 0. Like so, neural network architecture comparison shows from the okay and dual. The network contains a 20 blocks residential tower. I described the above, the followed by the policy head and value head. This architecture used in the AlphaGo 0, and we have so many neural network architectures we have. So without human interaction, by using the artificial intelligence, um, without without human interaction, we using the artificial intelligence, we design the games. So this is the conclusion of this paper. So thank you. I think it's okay.